Okay, I think we can start. Our final talk before lunch will be on MHD simulations of neutron star mergers, and it will be given by Kota Hayashi. Kota is a senior postdoctoral researcher at the AEI, and his focus is compact binary mergers. Kota, I'll let you know once you have 5 minutes left before questions. So
Yes,
you can start whenever you're ready.
yes. Thank you for that. Thank you for the introduction, and thanks for giving me the opportunity to talk about my work today. And sorry for my voice today. I'm having a sliced sore throat, so I apologize if it's difficult to hear what I'm talking. Yes. So as an introduction, I think I cannot avoid talking about these events on the observing compact binaries merger using the gravitational waves. Of course, the gravitational wave astronomy has begun on the 2015 for the black hole binary system. But as my talk title shows today's title shows my interest is the binaries that includes the neutron star, which shown here that which is expected to have the electromagnetic counterpart, and the first binary neutron star event was likely the one that has the electromagnetic counterpart, the short gamma ray burst, the kilonova, and yes, this event has uh, pro, accelerated our multi-messenger era for us. And after this event, we also had a binary neutron star event, GW190425. Unluckily, this one did not came up with the electromagnetic counterparts, but this one is quite a unexpected event in a sense that the total mass of this system was 3.4 solar mass. It's a quite heavy one, which we have a quite a good consensus that it promptly collapses to the black hole right after the merger. But even though this one did not came up with the electromagnetic counterpart, we expect the electromagnetic counterpart from the similar source could be detected if the mass asymmetry is large and the sky localization is better. This event was not did not have a good sky localization. So yeah, in a sense that it was quite an unlucky event. And here's a overall picture of the types, the categories of the binary neutron star mergers. The GW700817, which I showed in the previous slide. This one, that event seems to be in this path, which goes right after the merger. It forms the hypermassive neutron star, and due to the hydrodynamic and viscous evolution, it gradually collapses to the black hole and forms a black hole and disk system. On the other hand, this the 900425 event, which has a huge mass, that event, we think that it has a prompt black hole formation. And so, yes, we have a black hole formation right after the merger. And depending on the mass ratio of the system, we have a if the mass ratio is quite small, I mean, in a sense that the two object has a quite similar mass, we expect the system to have a no significant materials remaining after the merger outside of the black hole. But if we think that this event has the quite high mass ratio, we expect to have a black hole and disk system. So our interest, I mean, our focus is the case that has the significant mass remaining outside of the neutron star, sorry, the significant mass remaining after the merger around the compact object. And yes, our group have been doing the series of simulation to cover these kind of system and try to model the post-merger post-merger phenomena and signals, electromagnetic counterpart signals coming from these kind of phenomena. And not only the binary neutron star mergers, the black hole and neutron star merger has been detected by the LIGO Virgo gravitational wave observation, the 200115. Yes, this one was the first BHNS merger. Unluckily, this one did not also like the 90/25 event, no electromagnetic counterparts were detected. But if the spin is quite large, then there could have been a quite significant mass remaining outside the black hole, which could also have a high expectation for the electromagnetic counterparts. And additionally, the 23/0529, this one, yes, this one, we think that it is a black hole and neutron star system, but to be accurate, the primary object has the mass of 2.5 to 4.5 solar mass. And so it means this mass range is the mass range that we have not detected we have not discovered the compact object existing from the previous observation. So yes, this one is somewhat rather the unknown object still, but yes, considering the limitation, considering the GW700817 event, we think that this this object could be the low mass black hole, which have never been discovered. And for the black hole neutron star merger, so yes, black hole neutron star merger, we think that these kind of things happens depending on these kind of parameters. So if the black hole spin is larger, the neutron star radius is larger, or the mass ratio is smaller. And here mass ratio means that black hole mass over the neutron star mass. In these cases, we expect that the neutron star is tidally disrupted by the tidal force of the black hole. And in this case, we expect to have the electromagnetic counterparts. And in this sense, if you think about the mass ratio, this model, I mean, this event is a low mass, as I said, it's a low mass black hole event, meaning that this mass ratio is quite small. Yes, if we could have pinned down the location of the source, yes, I think that it could have been a nice candidate for the electromagnetic counterparts accompanying the gravitational wave event. And why this neutron star, I mean, the compact binary mergers, including a neutron star, is interesting, is that, yes, I think it's quite a well-known fact. I am listing the well-known fact for you here, but yes, the neutron star, the gravitational wave carries information on the neutron star equations, and the heavy element could be synthesized in the neutron star, a neutron-rich ejected during and after the merger, and it shines as the kilonova. And if the merger remnant is a spinning compact object with a magnetized disk, then this could be the nice central engine for the short hard gamma ray burst, one of the kind for the most energetic explosive phenomena in the universe. Yes, so yes, this binary neutron star, I mean neutron star compact binary merger, including a neutron star, has been our interest for a long time. However, there was a problem for the previous simulations. For the merger simulations, the simulation starting from the inspiral phase, it was often the case that the too short for studying the post-merger stages. So many of them were essentially focusing on the gravitational wave emissions. So yes, it was focusing on the in-spiral stage to the shortly after the post-merger stage. But as I will be talking later on, in order to have the self-consistent full picture of this merger system going up to the post-merger, then the second long simulations are required. Another case is that some of the physical inputs were absent, in a sense that for example, the MHD, the magnetic field effect, were somewhat modeled by the viscous simulations. But in order to have the full picture, again, we also have to have the general relativistic neutrino radiation MHD simulations required for giving us the nice full picture. And yes, in order to cover the drawbacks of this short simulation. There have been a black hole and disk the simulation starting from the black hole and disk, but the initial conditions could be the artificial. For example, the magnetic field configuration right after the merger could be somewhat artificial, and the realistic picture might have not been obtained for this kind of system, for this kind of simulations. So in order to overcome these problems, our groups have been doing these kind of simulations, the 3D GRR, general relativistic, numerical relativistic, neutrino radiation, MHD simulations for the neutron star binary mergers and the accretion disk system formed after the merger. So as this shows, we have in our simulation, we have the full GR included, the neutrino radiation transport, and the ideal MHD included in our simulations. And yes, I have to note that our code is independent from the Einstein Toolkit, which has been our simulation code has been developed by the Kyoto University group and currently by the AEI group for more than, I think it was 30 years. It has a history of about 30 years or something. So yes, the one important point for our simulation that it has this kind of all necessary physical input were included in our simulations. And another important point that I have to mention here, as I mentioned previously, is that the timescale of the simulations, we have done these simulations starting from the in-spiral stage to the post-merger stage, and this post-merger stage covering up to the scale of the second. And why this second scale is required is to cover up all the important mass ejection phenomena. One is dynamical mass ejection, which has a time scale of 10 milliseconds. But yes, this one has been covered. This one has been intensively studied by the previous numerical relativity simulations, focusing on the early post-merger, focusing up to the early post-merger phase. And another thing, the post-merger mass ejection in the form of like a disk wind. And this post-merger mass ejection is known to have a time scale about a second, which is driven by the viscous effect. So the previous viscous hydrodynamic simulations have shown that the second, about 1 second, is a time scale that is necessary for covering up the post-merger mass ejection. And the timescale of the short gamma burst, this one essentially coming from the observation, but the short gamma burst is known to have the timescale of 1 to 2 seconds. So yes, in order to cover up all these important phenomena in one self-consistent simulations, we have done the simulations from in-spiral stage to the post-merger stage of extending up to seconds. So yes, I would like to show the results here. The result the things that I will be talking here today is about the black hole and neutron star merger and BNS binary neutron star merger with the prompt black hole formation. But yes, in the question, I will also be happy to take a question not only limited to this, but also the other kind of black hole, other kind of binary neutron star system. So to give you the overall sketch of what we get in a simulation, I would like to show you the animation. Currently, I'm just showing you the snapshot to explain what I'll be showing. I will be showing the snapshot, the animation for the rest mass density. This contour is going to be showing you the rest mass density contour. And the pink line will be showing you the magnetic field line penetrating the apparent horizon. And the green arrows will be showing you the magnetically driven unbound materials. So yes, we have first had the binary in spiraling and it merges, and due to the yes, I should have mentioned that this animation is for the promptly collapsing black hole binary neutron star merger system. So yes, right after the merger, we have the mass expanding. These mass are the dynamical mass ejection ejected by the tidal force uh, applied by the heavier component. And yes, we have the black hole and the disk formed. And in this disk, we have the magnetic field amplified. And gradually, we have a large-scale magnetic field generated, penetrating the black hole and forming the magnetically dominated region in a bipolar form in the black hole spin direction. And within this magnetically dominated region, the magnetically driven outflow, I would say the jet. The jet is launched in the polar region, which will be generating the short gamma ray burst. And it is somewhat difficult to see in this kind of animation, but the post-merger ejection is launched from this disk system, making this disk unbound and unbound from the system, gradually expanding to the outer side. So more into the detail of the result, I will be first showing you the black hole and neutron star merger. The model that I have done a simulation is this kind of things. The black hole mass having a 5.4 solar mass. The neutron star mass is 1.35 solar mass. This mass is motivated from the GW200115 model, which in the mass distribution figure, it is located here. So yes, it is consistent with the GW0115 models. But in order to have the sufficient tidal disruption, we have given the black hole spin to be 0.75 and the neutron star radius to be quite large, that's 13.2 kilometers. And in order to make our simulations reliable, we have done several simulations making the initiating from the different maximum magnetic field strengths superimposed inside of the neutron star. In our simulation, the magnetic field is confined in a neutron star. The maximum magnetic field strength ranging from like 3 times 10 to 15 Gauss to like 5 times 10 to 16 Gauss. And we also have a different resolutions. We also assume the different equatorial plane symmetry, I mean with and without equatorial plane symmetry imposed. So more into the detail of the result, yes, I am showing you here how the magnetic field is generated in the disk during after the post-merger evolutions. This panel showing you the magnetic field over internal energy, and you see that well, I have a different model, but maybe we can just focus on this purple one with the magnetic field initiated magnetic field with the 3 times 10 to 15 Gauss. This case, yes, we originally have this magnetic field energy over internal energy to be like 10 to minus 4, 10 to minus 3, but it gradually amplifies due to the MRI, magnetorotational instability, and the winding and the Kelvin-Helmholtz instability. It amplified quickly, and it saturate at around 1%. I mean, magnetic field energy amplification saturated at around 1% of the internal energy. And at this point, at this equiprotation, this is at this saturation regime, the MRI induced effective turbulent viscosity evolves. Sorry, the MRI-induced effective turbulent viscosity evolves the system, evolves the disk, and this panel showing you the effective viscous tensor, defined by the Maxwell stress tensor over the pressure. which can be thought as the Shakra-Sunyaev alpha parameter used in the viscous hydrodynamic simulations. This value going up to about 0.05, giving us the about 1 second of the time scale for the viscous turbulent evolution. And due to this effective turbulent viscosity, the disk evolves, and due to this effective viscous heating, the post-merger mass ejection is powered. And it's in this case, the mass of the post-merger mass ejection goes up to 0.03 solar mass. About 10% of the disk shown you here is the ejector mass. So at the first point, at a time scale of like several milliseconds to 10 milliseconds, we have an initial mass ejection, which corresponds to the dynamical ejector driven by the tidal force. And from there, taking about several hundred milliseconds, we have the plateau phase. And from around here, about 300 to 500 milliseconds after the merger, we have another increase of the ejector mass, which corresponds to the post-merger ejector. And you see that we have the about 0.03 solar mass ejected from the system. And going on to how this post-merger mass ejection is driven, I would like to first talk about the neutrino luminosity and the temperature of the disk. Here I'm showing you the neutrino luminosity evolution. And originally it has, right after the merger, it goes up to like 10 to 53 L per sec, and it gradually decreases. And this decrease is due to the decrease of the temperature. And this orange arrow is showing you the time of the post-merger mass ejection launch. This corresponds to about 10 to 51 to 10 to 51.5 L per sec. And going on to the temperature, again, this orange corresponds to the post-merger mass ejection launching time. And this panel showing you the mass distribution on the time temperature diagram. And this shows that as the temperature decreases and this mass ejection time correspond to when the maximum temperature of the disk goes below about 3 MeV. Yes. So considering these facts about the neutrino luminosity and temperature, I will just give you the sketch of the mechanism for the post-merger mass ejection. Due to the, as I just mentioned, due to the MRI viscous heating, the thermal energy is generated. I mean, due to MRI viscous heating, we have the due to the MR viscosity, we have the angular momentum transported from the inner part to the outer part of the disk, making the matter to be accreting onto the central object. And during this process, yes, the thermal energy is generated. However, when the temperature of the disk is larger than 3 MeV, then the neutrino emission is high, and that it carries out the generated energy away and cannot be used for the mass ejection, and thus the matter will not be ejected in this phase. But yes, as I mentioned, due to the MRI viscosity, the angular momentum is transported and the disk gradually expand, and during this process, the temperature of the disk gradually decreases. And neutrino, due to that drop of the temperature, the neutrino luminosity also drops in proportion to the temperature to the power of 6, meaning that the neutrino luminosity quickly drops, and when the temperature of the disk gets below 3 MeV, and then what this shows here, what temperature evolution and the disk post-merger evolution shows is that when the temperature drops below 3 MeV, then the generated energy can no longer be and the generated energy can no longer be carried away by the neutrino, and thus will be used for the making the disk matter to be unbound from the system, from the remnant black hole. And here I am showing you the property of the ejector in this system. here I'm showing you the electron fraction of the ejector. We have the two distinct components. One is for the dynamical ejector, which have the low YE. This one, since the black hole and neutron star merger, since the dynamical mass ejection of the black hole and neutron star merger does not include the thermal process, it is only ejected by the tidal force. So it will not be, this dynamical ejector will be carrying the property of the neutron star that originally had. So it has the low YE, lower than 0.1. But for the second component, post-merger component, has the YE ranging from 0.1 to about 0.4 and having a peak at 0.25. Yes, since as we talked, since this post-merger ejector is driven by the thermal process, yes, this has the higher YE compared to the dynamical ejector. And here I'm showing you the velocity of this ejector. This one also we can see the two distinct component. One is dynamical ejector component ranging up to 0.4, 40% of the speed of light. And this component here, the slower component, this one is a post-merger ejector. And based on this based on these properties of the ejector, the nuclear synthesis study have done, and it showed that it can reproduce the solar-like process pattern. So up to here, I have talked about the property of the ejector. I mean about the dynamical ejector and post-merger ejector. Now I would like to talk about the jet launching that could possibly power the shortcut burst. But yes, since our simulation initiated from the neutron star, since we have started the simulation having a magnetic field to be confined into the neutron star, we do not have any large-scale magnetic field extending up to the several thousand kilometer scale that can generate the magnetosphere and the jet launching. So we have to think about how the magnetic field, large-scale magnetic field can be generated. Here I'm showing you the azimuthally averaged toroidal magnetic field. And in the time polar angle diagram showing you the different color, I mean red and the blue showing you the opposite polarity. And what we see here and here 0 pi here is showing you the polar region, this 0.5 pi region, this showing you the equatorial plane region, which correspond to the disk. And within the disk, we have a periodic generation of the magnetic field, and it gradually propagates to the polar region accumulated there. But yes, at this stage, it is still not a large-scale magnetic field. Yes, it is true that the mean magnetic field, since it is a average toroidal magnetic field I am showing you here, this indicates that the mean magnetic field is generated in the disk. But it does not necessarily mean that it is a large scale. So we have to also think about how the large scale magnetic field is generated here. The short answer here is that the magnetic tower effect plays a role in forming a global magnetic field in the polar region. So I'm showing you here the snapshot of the large-scale magnetic field generation process. Yes, originally, yes, as we have talked here, the mean magnetic field generated in the disk propagates to the polar region, yes. And it will be penetrating the black hole. And so due to the spin of the black hole, the magnetic field is further, the toroidal magnetic field is further amplified, making the magnetic pressure in this polar region to be enhanced. And due to this enhanced magnetic field, it pushes itself and also the matter around here, it pushes the magnetic field itself and the matter around here to the polar region, making this magnetic field to be extending to the bipolar form, and it will eventually form the large-scale magnetic field. And since we have the high magnetic field here, high magnetic field in this polar region, but the matter will be pushed away from this region, or it accretes onto the black hole, this polar region will be the magnetically dominated region, and it will have the magnetosphere. It will result in a magnetosphere. And within this magnetosphere, the Poynting flux is generated near the black hole rotation axis. And this Poynting flux property is found to be consistent with a short Gamma ray burst. Showing you here is the Poynting flux distribution on the sphere with a radius of about 1,500 kilometers. And this shows us that at the polar region here, we have the collimated Poynting flux distribution here with the opening angle of about 10 degrees. And here showing you the isotropic equivalent luminosity evaluated, also evaluated at about 1,000 kilometer scales extraction radius. This shows us that the isotropic equivalent luminosity is reaching up to 10 to 50 to sometimes 10 to 51 L per sec. This one also consistent with the short Gamma ray burst. And it is not very clear, but we start to see the luminosity decrease starting at 0.5 to 2 seconds. And yes, this time scale is also consistent with a short Gamma ray burst. So summarizing up these three features seen in our simulation for the Poynting flux is consistent with a short Gamma ray burst. And one thing, how this Poynting flux is generated, the short answer will be the black box logic mechanism. This panel shows you the Poynting flux, this Poynting flux distribution and this. Sorry, this orange showing you the outgoing Poynting flux, the blue contour showing you the ingoing Poynting luminosity, and this white line showing you the poloidal magnetic field line. And it might be difficult to see, but this black circle here showing you the apparent horizon. So what this panels means is that along the magnetic field, the outgoing Poynting luminosity distribute from the surface of the black hole extending to 100 kilometers. And yes, it is also extending up to several thousand kilometers. So what this means is that what is indicated is that the energy is extracted from the rotating black hole to the magnetic field. And this indicates that the blind force logic mechanism is powering this Poynting flux. So we have, up to here, I have talked about the black hole and neutrons Martian systems. I will also be talking here from now on is that the black hole and, the binary neutron star with the prompt black hole formation. But to be honest, since we have the black hole formation right after the merger, this system is somewhat quite close to what we have in a black hole and neutron star system. In the for the model primary side here, we have the 1.25 solar mass and 1.65 solar mass, and the neutron star to be SFHO. It's quite a soft EOS. So thinking about this parameter, this model will be collapsing to the black hole right after the merger. It has a prompt black hole formation. And as we have talked in the introduction part, this model have a quite large mass asymmetry. So this will be having a large significant mass remaining outside of the black hole after the merger. And again, the magnetic field, the maximum magnetic field strength is 10 to 15 Gauss confined in the neutron star, and we assume the poloidal magnetic field. And in this simulation, the equatorial plane symmetry is not imposed. And here I show the MRI quality factor in the region where the density is lower than 10 to 10 gram per cc, meaning that this orange, green, red, purple line shows us that even from the right after the merger, about 10 milliseconds after the merger, we have the MRI quality factor to be exceeding 10, meaning that the MRI, the fastest growing mode of the MRI, is resolved by more than 10 grid point, meaning that the MRI is, I would say, sufficiently resolved. But for the highest density region with 10 to 11 gram per cc, the MRI is not fully resolved for the initial 100 millisecond. But yes, right after the, after 100 millisecond after the merger, we have the MRI quality factor to be exceeding or reaching up to the 10. So we have to, I would say that the evolution after the 100 millisecond is reasonable enough.
You have 5 minutes left.
Yes, thank you. And as the MRI is resolved, as in the case of the black hole and neutron star system, the turbulence is initiated. The turbulent state is initiated, making the Shakra-Sonia's parameter of the disk to be exceeding 10 to 0.01, making the disk to be evolved by the viscosity. And due to the MRI, as in the poloidal magnetic field is generated. What we have seen in the BHNS cases is that the toroidal mean magnetic field is generated, but we have confirmed in this simulation that the toroidal mean magnetic field is also being generated, which is rather more essential for generating the magnetosphere in the jet. So here I'm showing you the rest mass density, poloidal magnetic field, MRI quality factor, and the Maxwell stress tensor. And maybe we can focus on this one. We see that the magnetic field, the mean poloidal magnetic field, is generated within the disk, propagating to the polar region, accumulated there. And I will be showing later on, but again here we have the large scale magnetic field generated, resulting in the magnetosphere. So yes, what I have shown here is that yes, we have a cycle of mean large scale magnetic field generation with the omega effect, the effect of the toroidal magnetic field generation from the poloidal component by winding, and the alpha effect, the poloidal magnetic field generation effect from the toroidal component by the MRI-driven electromotive force. And what we have confirmed in our simulation is that the period of this magnetic field generation. So we have seen that there was a periodic magnetic field generation, red, blue. This periodic magnetic generation, the period of this magnetic field generation is consistent with the alpha omega dynamo theory. And yes, actually there were more than 3 periods of alpha omega dynamo polarity flip until the magnetosphere formation. So I can strongly say that the alpha omega dynamo strongly contributes to the magnetosphere formation. And yes, within this magnetosphere, we have again see the pointing flux launch. In this case, the the pointing isotropic pointing luminosity reaching up to 10 to 49 L per sec, which is a little bit weaker for the typical short gamma burst, but I would say it's strong enough for some kind of low luminous short gamma burst. So yes, maybe I will be skipping this one, but maybe you can ask me a question about it here. So the summary here, yes, we have done the 3D generativistic neutrino radiation magnetohydrodynamic simulation for the neutron star binary merger through the in-spiral stage to the long evolution of the post-merger stage. We have confirmed that the MRI-induced effective viscosity, MRI-induced effective turbulent viscosity controls the evolution of the disk system, and it launches the post-merger ejector. It also results in a large-scale magnetic field generation and the formation of the magnetosphere. And within this magnetosphere, we have found that the pointing flux consistent with the short gamma ray burst. Yes, thank you.
Thank you very much for the very nice talk.
Thank you.
So we have time for a couple of questions. I see Stefan Rosewalker is